Welcome back for another deep dive.
Yeah.
Today we're going to be talking about something I think that's on a lot of people's minds, and that is earthquakes.
Yeah, definitely. I think after what happened in Turkey earlier this year, it really kind of
Right.
brought it all back.
I mean, those 7.7 and 7.6 magnitude earthquakes were
Yeah.
just devastating. And it's a stark reminder, I think, of how vulnerable our buildings really are.
Absolutely. And it's interesting because a lot of the devastation was due to a lack of what engineers call ductile detailing.
Right.
And just poor construction practices in general.
Yeah, and over 50,000 people lost their lives,
Yeah,
and there were 1.5 million people displaced.
it's incredible.
It's really tragic. So it really raises the question, can we design buildings that can withstand these forces
Yeah.
and be better for the environment?
Right. Can we have both? That's the question. And it's particularly relevant, I think, for places like Quito, Ecuador,
Right.
which is also in a very seismically active zone.
Yeah, and they had that 7.8 magnitude earthquake back in 2016, which also caused a ton of damage.
Mm.
So for this deep dive, we're going to be looking at a research article
Okay.
that analyzes this exact problem.
All right.
They looked at a typical 7-story building in Quito
Okay.
and compared 3 different structural systems to
Right.
see how they hold up in an earthquake.
Right.
And they also used something called the life cycle assessment, or LCA,
Right.
to evaluate the environmental impact of each system.
So basically, like calculating the building's carbon footprint from the get-go.
Exactly.
Yeah.
So before we jump into the specifics of how they did this,
Yeah.
I think it's important to understand the problem we're trying to solve here.
Right. Well, I mean, the problem is twofold, right? First, we have to make sure that the buildings can withstand these massive forces from earthquakes.
Right.
And the thing about earthquakes is not only do they cause immediate devastation, with collapsing buildings and all that, but there's a lot of environmental damage that happens afterward as well.
Oh, absolutely.
Think about all the debris, the resource-intensive repairs that have to happen afterward. It's a whole cycle that just keeps adding to the environmental burden.
Right.
And then secondly, we have to consider the impact of the construction industry itself.
Right.
The construction industry contributes something like 40% of global annual carbon emissions.
It's a huge amount.
It's a massive.
Yeah.
So the challenge is to find that sweet spot between making sure buildings are safe, but also being mindful of the environment.
So it's not just about making buildings stronger. It's about making them stronger
Right.
in a smarter, more sustainable way.
Exactly. And that's where this whole concept of optimization comes in.
Yeah.
Just building stronger often means using more materials,
Right.
which, as we know, usually translates to a bigger environmental footprint. And that's where this LCA, the life cycle assessment, comes into play.
Right.
It helps us quantify the impact of all of that from the very beginning.
And you mentioned that this research kind of fills a gap.
Yeah.
What exactly were they looking at
Okay.
that wasn't already known?
So the idea of LCA, this life cycle assessment, it's been around for a while, but there isn't a ton of research that looks at how different structural systems affect both the seismic performance and the environmental sustainability at the same time,
Okay.
especially in developing countries like Ecuador.
Got it.
So this study's trying to look at that, what are those trade-offs?
So can we have our cake and eat it too?
Exactly.
Can we have a building that is both safe in an earthquake and doesn't totally destroy the environment?
And to answer that question, they picked a very specific case study in Quito.
Okay.
Can you tell us a little bit about that?
Yeah, so the building is in an area called La Carolina,
Okay.
which is known to have a pretty high seismic risk.
Right.
And to give you an idea, it's located at this latitude and longitude, negative 0.178332 degrees and negative 78.436299 degrees.
Very specific.
It's 26.5 meters tall, including the basement,
Okay.
and it's built on soil that has a bearing capacity of 0.18 megapascals.
So when we think about these specifics, it really paints a picture of the kind of challenges engineers face when they're designing in that region.
Exactly. And it's not just any random building they picked.
Yeah.
This is a very typical building
Okay.
for that area,
Got it.
which means that these findings can be applied to a bunch of different structures,
Right. Which makes it more relevant.
making it more useful for real-world construction.
Exactly.
So we've got our problem, we've got our case study building,
Yeah.
and we've got our 3 structural systems,
hmm
the OFS, the ODS, and the EFS.
Okay.
Can you break those down a little bit more for us? What are the key differences between them?
Absolutely. So let's start with the OFS. That's the optimized framed system.
Okay.
And essentially, as the name suggests, It relies primarily on a framework of beams and columns to resist the lateral forces you get during an earthquake.
Okay.
So you can think of it like a skeleton
Right.
that's designed to flex and bend
Right.
and absorb that energy without just totally collapsing. And this is a very common system in Ecuador because it's relatively easy to design and construct using materials they have readily available.
Makes sense. So what about ODS then? How's that different?
So ODS takes that frame system and adds to it.
Okay.
ODS stands for Optimized Dual System. And so it incorporates these things called shear walls in addition to the frame.
Okay. So shear walls are basically these reinforced concrete walls.
Yeah, exactly.
Okay.
They're placed very strategically within that building's frame.
Gotcha.
And they act like a really stiff internal bracing system.
Right.
So they really significantly increase the resistance to that side-to-side movement.
So the OFS is relying on kind of flexibility
Yes.
to absorb energy.
Right.
And the ODS is kind of adding stiffness in there to stop that from happening as much.
Exactly. Yeah. So there's less movement
Right.
and hopefully less damage.
So it's like a second line of defense.
Yeah, you could think of it that way.
Yeah.
And this is important because the ODS is trying to limit something called story drift.
Story drift.
Story drift, yeah, what's that? So story drift, it's basically the horizontal displacement of one floor relative to the one below it
Okay.
during an earthquake.
Got it.
So the bigger the story drift, the more likely you are to see structural damage or even collapse.
So ODS is trying to keep those floors from moving so much.
Exactly. Yeah, less story drift, less damage, more safety.
Gotcha. So what about this EFS? You mentioned it was kind of a hypothetical system.
Yeah.
Why include it at all if it's not actually something that would be built?
Right. So the EFS, or equivalent frame system, it's kind of like a benchmark in this study.
Right.
It's designed to be super rigid, like so rigid that it achieves that same level of drift as ODS.
Okay.
But the thing is, it would take an insane amount of material to build something like that.
Right.
So it's not really practical. It'd be
Yeah.
super expensive
Yeah.
and, not very environmentally friendly.
So by comparing the ODS to this EFS,
Right.
they can show that you don't have to go to these crazy extremes
Yeah.
with materials to get the same kind of performance.
Exactly. It shows that you can be efficient with your materials
Okay.
and still achieve a high level of safety.
So how did they make sure that this was a fair comparison between these three systems?
Well, first off, they used Ecuadorian building codes and standards throughout their whole analysis.
Makes sense.
They actually specifically looked at materials that are common in that region.
Okay.
They're mainly concrete, steel, rebar for reinforcement, and then wood formwork.
So really paying attention to
Yeah.
the details of how they actually build things in Ecuador.
Exactly. And that's important because it makes the results a lot more accurate and relevant to what's actually happening in the real world.
Awesome. So let's talk about how they actually measured
Yeah.
the environmental impact of each system.
Sure. So they used this detailed methodology that involved quantity takeoffs.
Okay, so quantity takeoff.
Quantity takeoffs.
What is that?
So basically, they calculated the precise amount of every material needed
Sure.
for each of the three systems,
Okay.
like down to the kilogram.
Wow. So they really went into detail,
Oh.
like an ingredient list for each building.
Pretty much, yeah.
Okay.
But that was just the first step.
Okay.
Once they had all those quantities, they used these things called emission factors.
Wait, emission factors.
Emission factors, yeah.
I'm not familiar.
Okay, so emission factors are basically like coefficients
Okay.
that tell you how much greenhouse gas is emitted
Right.
for a specific activity or material.
Okay.
So, for example, there's an emission factor for producing 1 ton of concrete,
Right.
another one for transporting it
Yeah.
to the construction site, all that kind of stuff.
So they're really looking at every step of the process,
Right. They're considering the whole life cycle.
not just the finished product. Right.
Exactly. Yeah. And all of this is laid out in the paper.
Cool.
For example, tables 5 and 6 show how the quantities of materials like the concrete, the steel, the wood, even the amount of soil they have to remove during construction.
Okay.
That all varies significantly.
Depending on which structural system they're using.
Right. Exactly.
Yeah. So I'm just curious, based on what we've talked about so far,
Yeah.
which system do you think ended up using the most materials?
I think you probably have a good idea.
But we'll save that reveal for part 2 of our deep dive,
We will.
where we'll look at the results and see which system had the biggest environmental impact and why.
Sounds good. All right. So let's get to those results then.
Okay.
Remember we were talking about quantity takeoffs and how they measured all the materials? Well,
Right.
as we kind of suspected,
Yeah.
the EFS, the hypothetical super rigid system,
Right.
That was the one that used the most materials by far.
Yeah, I guess that makes sense. If you're trying to make something super stiff, you're going to need a lot of stuff.
Right, exactly.
Yeah.
But the question is, how did that translate to its actual environmental impact?
Yeah. What did the LCA actually tell us?
Well, the LCA showed that the EFS had the highest carbon footprint
Okay.
out of all three systems.
Okay. And by how much?
It produced something like 39% more carbon dioxide emissions.
Wow. 39%. That's a lot.
It's huge, yeah.
Yeah.
So building super strong definitely doesn't equal eco-friendly.
Okay. So strong doesn't mean green.
Nope, not in this case.
So what about the OFS and ODS? How did they stack up against each other?
So the ODS actually had slightly higher emissions than the OFS.
Okay.
About 5% more.
All right. So not a huge difference.
No, not a huge difference. And then when it came to energy consumption, during the construction phase, ODS used about 6% more energy.
So from an environmental perspective, they're pretty close.
Yeah, pretty similar. But what about earthquake resistance? I mean, that's the whole point of this.
Yeah, that's what we're really concerned about.
Right, exactly. And this is where the ODS really shines.
Right.
Remember how we were talking about story drift?
Story drift. Yeah, that horizontal movement of the floor.
Right, exactly. Okay. So the ODS had a much lower story drift compared to that OFS.
And just to remind our listener, lower drift means less damage.
Less damage, yeah.
Yeah.
And potentially, fewer injuries,
right.
Saving lives.
Okay, so how much lower was the drift?
So the ODS had a story drift of just 0.82% compared to 1.75% for the OFS.
So almost half.
Yeah, pretty much.
Yeah.
And that difference, in an earthquake,
right,
that could be the difference between a building staying up and collapsing.
Okay, so the ODS looks like it's kind of the winner here.
Yeah, it seems to be that sweet spot between earthquake resistance and a relatively low environmental impact.
Okay, so why does the ODS perform so well?
So it really comes down to that clever combination of those frames and those shear walls we were talking about.
Right.
So you can think of the frames kind of like flexible springs that can absorb some of the energy.
Right.
And then the shear walls are those rigid supports that prevent the building from swaying too much.
So you got that flexibility and stiffness together.
Yeah, you need both to really resist those seismic forces.
It's not just about brute force.
Right, it's about smart design.
Okay, so what were some of the biggest contributors to the environmental impact across all three systems?
Yeah.
Like, was it a certain material?
Yeah, that's a great question. So the study found that material fabrication was actually the biggest culprit.
Really?
Yeah, across all three systems.
Okay.
It accounted for almost 90% of the total emissions.
Wow, 90%.
90%.
Yeah.
So even if you do everything right during the construction process itself,
the materials themselves are still a big problem.
Yeah, it all comes back to the materials.
Wow. Okay, so what were the worst offenders?
So when they looked at it more closely,
Yeah.
ready-mix, concrete, and steel rebar,
Okay.
those were the two materials
Got it.
that had the biggest impact.
So if our listeners out there and they see
Yeah,
a piece of rebar, they should think about its carbon footprint.
absolutely. Every little piece adds up.
Wow. Okay. So it's not just the materials themselves, but it's how
Yeah.
they're being used.
Exactly. And the study also pointed out how certain structural elements have a big impact. So things like the foundation beams, the columns, the slabs.
The core components.
Yeah, the main structural parts, those play a major role.
So we've seen that this ODS system seems to be a pretty good solution
Yeah,
for building in earthquake-prone regions.
it's promising.
Yeah. But does that mean that every building in Quito should be an ODS from now on?
Not necessarily. I mean, every building project is going to be a little bit different.
Right. There are different constraints
Yeah,
and requirements for every building,
exactly. So ODS might not be the best fit.
for every single situation.
Right.
So what are some of the main takeaways from this research?
Well, I think one of the biggest things is that we need more studies like this.
Okay.
We need more life cycle assessments, especially in developing countries.
Where there's not as much data available.
Exactly.
Yeah.
We need more data to really understand those trade-offs.
You can't just have a one-size-fits-all approach to this.
Right. Every region is going to be a little bit different.
Okay.
And the study also really highlighted the need for updated design guidelines. We need guidelines that prioritize both resilience
Right. We need both.
and sustainability. Building codes need to be updated.
To reflect the latest research.
Exactly.
Okay.
And of course, we always need innovation
Right.
when it comes to new materials and techniques.
Lower carbon concrete.
Yeah,
Yeah,
exactly. Recycled steel,
Yeah. Bio-based material.
all that good stuff.
So it's not just about picking the right system.
Right.
It's about looking at the big picture.
Yeah, that holistic approach to the whole building.
Okay. So For our listener out there,
Yeah.
knowing what we've talked about,
Yeah.
how would you approach
That's a great question.
designing a sustainable, earthquake-resistant building
Yeah.
in their own region?
Something to think about for sure.
So, before we wrap up this deep dive,
Yeah.
what are some things that our listeners should keep in mind
Okay.
when they're thinking about this problem?
Well, I think one of the first things is to remember that, different regions are going to have different challenges, different opportunities when it comes to building.
It's not like a one-size-fits-all kind of thing.
Not at all.
Mm.
What works in Quito might not work in,
Well,
say, California or Japan.
Exactly. You
Yeah.
really got to understand
Yeah,
what the risks are in your specific area.
absolutely. What's the history of earthquakes there?
Right.
What are the soil conditions like?
Right.
And how do the local building codes address seismic design?
You're not just designing in a bubble.
Right.
You have to think about
Yeah.
what's already there
Absolutely.
and what the regulations are.
Exactly. And then you also want to look into,
Yeah.
what materials and construction techniques are common in that region.
Right. Are there local sources for eco-friendly materials?
Yeah. Can you incorporate recycled materials?
Yeah.
Reclaimed materials?
Are there different construction methods?
Right. Are there things that
What would be better?
can minimize waste and emissions?
Right. It's kind of like a puzzle,
It is a puzzle.
trying to
man.
find the right pieces.
You got to find those right
Bring it
pieces.
together.
Yeah. And you have to balance all these different things.
Right.
Safety, the environmental impact, the cost aesthetics.
Right. It can't be ugly.
And it really takes collaboration.
Right. It's not just one person.
It's not a one-person job.
It's a team effort.
Architects, engineers,
Yeah.
contractors, policymakers, everybody needs to be talking to each other.
This has really opened my eyes to how complex it is
Yeah.
to design a building.
It's definitely a challenge.
Yeah. It's not just putting up some walls and a roof.
It's a lot more than that, especially when you're thinking about earthquakes.
Right.
But it's also a huge opportunity.
Right.
It's a chance to be innovative, to create cities that are not just safe from earthquakes, but
Right.
are good for the planet too.
Yeah. We've seen that it's not an either situation.
Right.
You don't have to choose between safety and sustainability.
Absolutely. We can have both.
And we need to strive for both.
We have to. And I think this ODS system
Yeah.
is a great example of that.
It shows that we can do it.
It gives us hope. It
Sure.
shows that we can build smarter.
So as our listener is going about their day today,
Yeah,
I hope they take a minute to look around at the buildings around them.
I hope so too.
Think about, the materials that went into them,
Yeah,
the energy it took to construct them,
right.
and what kind of impact they're going to have on the environment
Exactly.
long after we're gone.
It's something to think about for sure.
It's a sobering thought, but it's also empowering.
It is.
We have the knowledge and the tools to do better.
Yeah.
So let's make sure we're using them.
Let's build a better future together.
Absolutely.
Yeah.
Thanks for joining us for another deep dive.